This is a production of Cornell University.
So hi, I'm Liz, and I think Susan introduced my project pretty well. I've just been looking at temperature impacts in irrigated maize. And I'll start off by giving you a little background. So maize is the top cereal crop produced on a weight basis in the world, and it's of critical importance to food security and also to energy budgets. And because of that, there's a lot of interest in if maize cropping systems are going to remain as productive as they are today with a changing climate. There's a lot of local variability and uncertainty in climate projections, but there's consensus that air temperatures are going to increase in the coming century. And in the past decade, there's been a number of studies that have developed econometric models that are trying to look at these air temperature impacts on yields, whether we can make projections about maize cropping system yields based on air temperature alone. And some of these studies have come up with some pretty startling results. That first one by Schlenker and Roberts showed that based on a non-linear relationship with increasing air temperature and maize yields, we could see declines in maize yields up to 82% in the next century because of climate change. Lobel et al. In 2009 showed that maize yields have already dropped by 3.8% since 2009 after they adjusted for a yield trend in their data. And then Ariel Ortiz-Barbera, in a recent work that was challenging the validity of using a single climate metric to make these projections, warned that the growing consensus is that climate change impacts will largely be driven by exposure to heat. We also see some evidence that suggests that this is not the whole story. So, as you know, maize is grown in Argentina, Ecuador, Ontario. There's a lot of different temperature regimes where maize is being grown. And what constitutes a heat stress threshold in one place doesn't necessarily mean it's a heat stress threshold in another place. Similarly, we've seen that what constitutes a stressful temperature can change in one location from season to season. And so in some ways, the maize's response to heat represents an acclimation process. It's modified by prior temperature regime. Similarly, some other studies have come out that have shown that how we manage our maize cropping systems interacts with the temperature response as well. And there's been evidence presented that management can help to buffer some of these negative impacts from air temperature alone so that we have the ability to adapt our systems to the temperature. And probably most importantly, down here, a recent work by Susan Ria and Stephen Shaw over at SUNY ESF showed that if you're looking at irrigated maize cropping systems, this apparent response to temperature just about disappears, which suggests that previous models might have been conflating heat and water stress, which are, of course, often related in these systems. So what we were interested in doing is seeing if this econometric approach can be used to get at the mechanism of heat stress in these cropping systems. And our approach to doing this was to break the maize growing season down into growth development periods, which is not at all unusual. The idea here is that heat stress occurring at different points in maize growth and development is going to have a very specific, very different mechanisms that are contributing to that heat stress response that we're seeing in yields, and that different adaptation mechanisms would be needed to be developed depending on what that heat stress mechanism was. We also looked at more than just temperature with a little bit of nuance, because depending on how you break it down, multiple climate variables can come into play in helping you to determine exactly what that heat stress mechanism is. Another thing that we did, and I'm going to go a little bit more into detail about this later, is we modeled the duration of our growth development phases using thermal time instead of using set intervals for them. The reason here is we're looking at temperature stress. We're looking at when the temperature stress is happening in growth development. If those high temperatures are changing the duration of the growth development periods, we'd want to be able to capture that as an artifact. Also, increased rates of physiological development have been suggested as a heat stress mechanism in maize. So our objectives, once again, were to see if we could get at a maize yield response to high temperature if we were adjusting for these other confounding factors, such as management or, more importantly, moisture stress. We wanted to see if we could do a mechanistic analysis of this heat stress by looking at the timing of heat stress during crop development. And we wanted to see if we could quantify the potential adaptation from management and genetics. So we were able to do this using like an econometric model because we had a really amazing bank of yield data to work with. National Corn Growers Association is one of the 2 largest maize advocacy organizations in the US. And winners of the National Corn Yield Contest have consistently set world records for maize yields. So we got historical yield data from the National Corn Growers Association. We got all contest entries. And we kind of secured a data set where management has been optimized. You know, the goal of these growers is to get to that yield potential, the place where the only thing that's holding their yields back are climate and the potential of the cultivar. We only looked at irrigated classes. Once again, we wanted to control for the soil moisture stress. We looked at the states of Kansas, Missouri, and Nebraska for 2 reasons. We had a really high density of irrigated yields in these states. And also, especially with Kansas and Missouri, we're getting some of the highest temperatures that we're going to get in the Corn Belt. We looked from the years 2005 to 2012. Once again, for a few reasons. We had significant interannual variability in yields, also in climate conditions, including 2012, which was a very hot year. And we didn't have any significant yield trend that needed to be adjusted for. For our climate data, we used hourly climate data from the Missouri Mesonet and the High Plains Regional Climate Center. We had access to almost 70 weather stations in our study area. All this data had been quality controlled and gap filled. And we matched that climate data to our yield values based on proximity and also similar GDD zone. So once again, we're trying to make sure we're getting as close to accurate temperature conditions as we could here. From there, like I had mentioned before, one thing that I forgot to mention that was pretty important with the yield contest data, I'm just going to go back. We have access to the planting date and the cultivar, as well as a whole bunch of other management parameters. So the management parameters are important because one of our research questions were, you know, can we quantify the adaptation potential to any temperature impacts through management? The second thing that's important here is if we have the planting date and the cultivar, we can take that planting date to start our growing season. We can use cultivar specified GDD to maturity and to silking to model with pretty fine resolution what our growth development periods were using thermal time. So going back to our climate variables, we calculated temperature stress in a few ways that we found in the literature. We had hourly data, so we were able to calculate cumulative degree hours over different temperature thresholds. We looked at quite a few of them, but I'm going to talk here about 30 degrees and 34 degrees. So this is the amount of time that the crop spent in a temperature stress condition. We also have, with those variables, a 0 stress situation where we had no temperatures above that threshold. We use KDD. So KDD stands for killing degree days. It's often called extreme degree days too in the literature. This is the same thing as a normal growing degree day calculation, except for you're setting your base temperature at what you would consider your temperature stress threshold, and there's no upper limit. So that's cumulative degree days where daily Tmax was over 29 degrees C, because that's, once again, the value that's most often being used in the literature. We also looked at average night temperature, which is pretty self-explanatory, and cumulative solar radiation. And then for each yield value, we calculated this over the growing season and also during growth development periods. Once again, all of those durations were modeled using thermal time. Because we wanted to be able to quantify, I guess, the magnitude of yield response from climate impacts relative to other variables that we had access to in this data set, we used a mixed effects model. For fixed effects, we used planting rate, planting date, cultivar GDD maturity, and previous crop. Those were in the model because they were the most significant. We had random effects for cultivar, so that would be genetic variation that's not due to the maturity class. Location, once again, pretty self-explanatory. If there's any location-based trends in our yields. Farm ID nested in location, that lets us look at the difference between Farm A and Farm B that are in close proximity to each other. So that would be management level differences that we can't get at with our data, soils. And then we also looked at year of planting because we're specifically interested in seeing if we can explain any of the interannual yield variability that we know is in our data using climate variables. After we built this base model, our climate variables were tested as fixed effects, and then once again, we could get the relative magnitude of yield response out of that. So first, most of the studies that we're following up on looked at the accumulation of heat stress over the entire growing season. When we did that with our irrigated yields, we saw that none of our daytime temperature stress indices were significantly related to yields, which was a little bit of a surprising result. Radiation, as you'd expect, in irrigated maize under optimum management was significantly related to yields. And average night temperature was also significantly related to yields. When you look at these yield responses on a standardized scale, so change in standard deviations of predictor variable per change in standard deviations in yield, they're about equal in magnitude and inverse of each other. So we see that night temperature has an impact. Can we get at the mechanism for yield decline due to high night temperatures? So going back before, we did model the duration of our growing season using thermal time. We were trying to get at a potential heat stress mechanism, which is accelerated rates of phenological development by doing it that way. There's two kind of conflicting schools of thought about why night temperatures would impact yields. One is that increased night temperatures leads to night respiration, and the other is that increased night temperatures increase development rates. So you would, just like I spoke about, end up with less intercepted radiation per unit thermal time over the life of your plant. Because we modeled our growth periods using thermal time and we calculated our radiation variable by that model, we've kind of already captured that. We've kind of already captured the accelerated phenological development with radiation as the variable that would define it. So what we're looking for here is an impact of night temperature independent of radiation, and we didn't see one. So as far as we can tell with our data set and our method of analysis, we're not seeing an impact of, I guess, of night respiration, but our data seems to support the fact that the impact of night temperatures is increased rates of development. So we'll go from there. Once again, radiation was the most yield limiting climate variable. This just kind of illustrates that point with this data. The graph on the left shows our yields in blue by year, and then our distribution of radiation is shown in pink, also by year. And as you can see, they track each other somewhat nicely there. The graph on the right is the same thing, yields in blue, but the distribution of our high temperatures are illustrated in pink. And you see, like in 2009, low temperatures, high yields. 2012, where we actually had our highest yields in the corn in the yield contest data set, was actually also the hottest year in our record. So we know that radiation has the most explanatory power of any of our climate variables. We also know that it's correlated with high temperatures. The next question is, could the positive yield response from radiation be masking any impact of high temperatures? When we moved into our growth development phase analysis, we decided to look at radiation and high temperature at the same time in the model. We also picked TT34 because when we were modeling our thermal time, we had a cutoff on our GDD of 34 degrees. And so hopefully this would be getting at temperatures that we haven't already accounted for by increasing the rates of development there. When you do account for radiation in the model, daytime temperature does become significant, but it does so in kind of an odd way. During early growth right here, you see that TT34 and grain fill, or early growth and grain fill, high temperatures have a slight negative association with yields. But these came into the model as being significant with a crossed effect. So pretty much we saw that early growth radiation modifies yield response to high temperatures that are happening during grain fill. And I just said that wrong. Early growth exposure to stressful temperatures gives us a positive response to those same stressful temperatures if they happen again during grain fill. So if your crop wasn't exposed to any high temperatures in the spring, a big heat wave comes around during grain fill, you'll see a yield decline. As long as you've had consistently high temperatures, you actually get the opposite effect. It seems to be beneficial for yields. So a modification there may be of what's constituting a stressful temperature. The other thing that you see is that radiation remains significant. We see a positive estimate here. So these regression estimates, that's just the change in standard deviations of yield that would happen with one of those predictor variables. But you also see that high grain fill TT34 during high TT34 during grain fill negatively modifies the positive yield response you get from increasing radiation. even though we had significant climate effects, these climate effects are only explaining a very, very small amount of the total yield variance that we had in our data. So this right here is just yield variance explained by model effect. All of our random effects are in purple, our fixed effects are in green, and radiation and TT34, so all of our significant climate effects land about here. They only explain just under 6% of the total variance in the data set. To contrast that, like genetics, which you can find in this pool right here, other genetics, and also in cultivar GDD to maturity, so maturity class and then everything that's left over that explains yields besides maturity class, explained more yield variance than our climate variables did. Planting rate and planting date explained more yield variance than our climate variables did. Putting these climate variables into the model only explained about 15% of our interannual yield anomaly. So we still have a whole lot of interannual variance in our yields. And then what I want to point out right here is the farm level variance. So the difference between farm A and farm B that are neighbors to each other is a pretty significant pool of our variance here. And then the residual error, this is just like the traditional error term that you'd see in any linear model, was just over 30% of the total variance in the data set. So it's also noisy data. So you'll notice when I was looking at the regression coefficients before, I didn't point out that there was a significant temperature impact during silking, which is when at least I was expecting to see the strongest temperature impact. And overall, when you look at the entire population of cultivars, that's true. There was no significant impact of high temperatures during silking on yields. We broke our data set down to include only cultivars that had been represented by more than 10 yield variables, and then we test them to see if there was any significant cross effects between those cultivars and the temperature stress indices. So do any cultivars have a unique relationship with temperature stress? And we saw that yes, they do. Not very many of them, but there was a handful of cultivars that did appear to be sensitive to high temperatures during the sensitive period, as we defined it. But that with these cultivars that were sensitive, we saw the most variability in cultivar performance only under the no stress condition. So the cultivars that were significantly impacted by temperatures during the sensitive period, they performed about as well as everybody else under really stressful conditions, but they were the ones that were over yielding the rest of the pack under non-stress conditions. Creating this model that looks at cultivar as a fixed effect, it does not significantly improve our understanding of the temperature impacts over our model that has it as a fixed effect based on our model selection process. So I just note that this is just more anecdotal, and it suggests that maybe if there are still temperature sensitive cultivars out there, that could be taken into account, as part of adaptation mechanisms there. Then the last thing that we wanted to see was by altering our management practices, can we adapt to our temperature stress indices as we saw them, even though they were slight? And as far as we can tell, the answer is yes. So over here on the left, this is the, on your x-axis here you have early growth TT34. On the y-axis here you have grain fill TT34. And then the z-axis is yield response. And this is under average management, so just the mean of everything in our data set. Average cultivar to maturity, GDD to maturity, average planting date, average planting rate. If you have no stress in early growth, and then you increase your stress level during grain fill, your yields decline. High stress during early growth, high stress during grain fill, you get a yield boost. Go figure. And then same thing over here, except for now we've created a scenario that we called optimal management. So now we have just slightly increased our planting date. We've slightly decreased our planting date. We've chosen a higher performing cultivar that performed across a wide range of climate conditions. It was 33Y75, it was on that other graph. It was also a longer season cultivar. And we see that pretty similarly, no matter what, you just want to have high temperatures early in the spring, which makes sense because we're talking about an earlier planting date here. But the real thing that I wanted to point out here is that even slightly optimizing from within the range of current cultural practices, you're on a totally different scale than you'd see with your worst case scenario. Worst case scenario with slightly optimal management doesn't even overlap with best case scenario, average management. So this sort of tells us that within the range of temperature impacts that we're currently seeing, and we did see some really high temperatures in this data set, maybe the sky isn't falling, All right, so the conclusions. There's not much evidence of temperature sensitivity in irrigated maize. Night temperature was associated with decreased radiation and also with decreased yields. Radiation is the most yield-limiting climate variable that we saw in these systems. High temperature reduces the impact from increased radiation during grain fill, so we're not getting as much of that yield boost from more radiation if it's hot. But we also see that with our observed temperature impacts, we have evidence of acclimation. So prior temperature regime experienced by the crop is going to impact whatever its response is to temperatures later on. Climate impacts explain very little yield variance and can be compensated for by slightly optimizing management. And so, that just kind of brings me to my final point. Controlling for soil moisture, if you're going to be doing this type of econometric analysis to make yield projections in a changing climate, seems like it could be of some importance. I just want to thank everybody on my committee, and also Peter for all your help. I also want to thank, I wish he was here, Erica Murdrock, who was my consultant over the Cornell Statistical Consulting Unit. She's great if anybody hasn't had a chance to meet her. And then all the rest. Yeah, thank you very much.
This has been a production of Cornell University, on the web at cornell.edu.